Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska Fairbanks. Welcome to Unit 9, Wind and Weather. The first slide shows two maps, a global map showing the sea level pressure on 19th of October 2004, and the second map highlights the pressure in the Bering Sea. And what we see is a low pressure system in the middle of the Bering Sea with a central low pressure of 941 millibars. This was an intense storm that did significant damage to Nome. What I want to highlight in the pressure distributions are the change of pressure with distance. Near the center of the storm, a change of 21 millibars in 300 kilometers, and further out from the storm, a pressure change of 6 millibars in 300 kilometers. These changes in pressure are associated with the winds, where the change in pressure with distance, the pressure gradient is higher. We see much higher winds than when we are at lower pressure gradients in the edge of the storm. The other thing I'd highlight about this storm is you can see how unique it is in the northern hemisphere. There's no other deep, low pressure system like this anywhere in the northern hemisphere. There are a pattern of low pressure systems off the coast of Antarctica associated with the major storms that are found there, and when we look at the global circulation in Unit 10 we will see why these arise. Pictures of Nome show the view along the seafront in Nome. The yellow arrow associated with figure A shows the debris associated with a storm surge that came in on the city, and in B, looking out along the side of the building here, you see that the debris that came up on the street and past the building, there's the yellow building in A, the yellow building in the large figure, and the debris comes right into Main Street past the buildings along the seafront. Huge amount of damage in Nome, a major event in the history of the city. So the major question we're looking at in this unit are what forces control the speed and direction of the wind. Wind in some sense is the major part of weather that makes weather difficult, wind and precipitation. We talk a lot about temperature, we talk a lot about cloud cover, but it's wind and precipitation that make weather challenging. So the questions we're asking in this unit: what is wind? What are the forces governing the wind? And we'll talk a lot about force balance. How does the rotation of the Earth affect the wind? We see that the circular patterns of motion in the atmosphere reflect the fact that the atmosphere sits over a rotating planet. How does the surface affect the wind? Are the winds at the surface different or the same as the winds aloft, up high? How are they connected to each other? And finally, how do we measure wind? I will focus here on just fleshing out some of the radar work that we've seen in weather radar. There's a discussion of measurement techniques in the book chapter that's quite complete. So if we think about the atmosphere as a bathtub of fluid, we expect that the warmer fluid, if we're in a warm region, should expand higher than in a colder region. The air there should contract. So if we think about how the pressure changes in altitude in both columns, we see that in the tall column, to get halfway up the column from a pressure of 1000 millibars to 500 millibars, you're further up in the air than in the cool column, where you go from 1000 millibars to 500 millibars sooner because the air is colder and denser. And so we see that constant pressure surfaces are at different heights in different columns depending on whether they're warmer air or colder air, and therefore along a given height the pressure decreases as you go from warm air column to cold air column. And so we now have a pressure gradient, a change in pressure where I'm being pushed from the warm column to the cold column. This is a mechanistic description of why air flows from warm to cold. It fits, though, with our general principle that air has to flow from warm to cold regions because we have energy transfer from an excess of energy to a deficit of energy. And so we see two things coming together here: a mechanistic description of how air flows that fits with our general principle about thermodynamics and how heat and energy move in any system. This explains the method by which the wind carries energy from the tropics to the poles in a very simple understanding of the atmosphere that we will look at when we look at the general circulation. So the fundamental driver of wind is differential heating of different regions by different amounts that sets up different columns of air with different pressure distributions with height, and that sets up the pressure gradients that drive the wind. So the wind is a response to the differential heating of the Earth's atmosphere. This question of pressure at a given altitude changing with the temperature of the air column is a huge issue for Alaskan pilots. In a small Alaskan aircraft, we measure altitude by measuring the local pressure and then using a standard atmospheric conversion from pressure to altitude. So 700 millibars is a standard altitude of 10,000 feet. However, if we're in warmer air, you're actually higher up than that at 700 millibars. And if you're in colder air, you're actually lower. So in Alaska, when we get extreme cold weather, pilots are flying lower than the standard atmosphere as represented by their altimeter measurements. And so if they're flying close to the ground, this can be a big deal because they can fly into the ground unexpectedly. And that is why we ground small pilot flying in Alaska when it is extremely cold, because the danger is that a pilot coming into land will reach the ground sooner than they expected and we will have a major accident. Just a quick correction, we don't ground small pilots, we ground small aircraft. I wanted to discuss the Coriolis effect and the Coriolis force in more detail than it's discussed in the book, in terms of numbers, comparing the effective pressure gradients in a place like New Orleans at 30 degrees north where we see hurricanes, and similar pressure gradients in Nome where we don't see hurricane force winds. And I've taken Seattle as at an intermediate latitude just for comparison. So New Orleans is at 30 degrees north, Nome is at 65 degrees north, and Seattle by latitude is halfway in between at about 48 degrees north. In the plot on the left, I show for a given wind speed what we expect the Coriolis acceleration effect to be, the meters per second, the rate of change of speed. And you can see the numbers are rather meaningless. I don't think they'll mean anything to you. So what I've done on the right scale is convert that number into speed in miles per hour if that acceleration existed for 1 hour. And what you see is that far winds of about 50 miles an hour, whether you're at New Orleans, Seattle, or Nome, you produce Coriolis effects that after an hour you expect to give you winds on the speed of 15 to 25 miles an hour. So it tells you that the Coriolis effect on the time scales of meteorology over periods of hours is going to produce wind effects that are comparable to the driving winds, and therefore it is a serious effect. The plot shows the red line is New Orleans, the low latitude site, the green is Seattle, the mid-latitude site, and the blue is Nome, the high-latitude site, that at Nome we get more bang for our buck in the Coriolis effect, that we get a higher Coriolis force, and it's called a force because we frame the effect as a force in our mathematics to understand the balance of forces that make the winds work the way they do, to explain the winds as we see them in the atmosphere. So Nome, at high latitudes, we get higher Coriolis forces for a given wind speed. So if we can turn this around and say if we need a certain Coriolis force to balance other forces in our meteorology, then we can get that force for lower winds in Nome than in New Orleans. And so for a Coriolis effect produced by a 51 mile per hour wind in Nome, that takes a 92 mile per hour wind in New Orleans. And so higher winds in New Orleans associated with the same pressure gradient forces that are balanced by the Coriolis forces than in Nome. If I move to the right slide, I showed the kind of wind speeds we expect just above the surface, far different pressure gradients based on the Coriolis effect balancing the pressure gradient force. I take two examples. We saw in the Nome example that at the edge of the storm we were seeing pressure gradients of 6 millibars in 300 kilometers. That's 2 millibars each 100 kilometers. And we also saw near the center of the storm pressure gradients of 21 millibars in 300 kilometers, which is 7 millibars in 100 kilometers. And so for those pressure gradients we see that at the edge of the storm at Nome, we might expect wind speeds of about 28 miles per hour, and at the center of the storm, we might see wind speeds of about 100 miles an hour. Whereas, if that pressure system had existed, that low pressure storm had existed with those pressure gradients in New Orleans, at the edge of the storm we would see 50-mile-an-hour winds, and at the center of the storm we would see 180-mile-an-hour winds. And so what we're highlighting here is how the pressure gradient force, when it's balanced by the Coriolis force, gives us different wind speeds with different pressure gradients, and also how we can have hurricane-style systems in Alaska that do not give us hurricane force winds because of latitude. So this balance between the pressure gradient force and the Coriolis force gives rise to what we call the geostrophic or earth-turning winds. In the panel on the left, we see a side view of the atmosphere, a warm region in A, a cold region in B. The 900 millibar surface is higher at A than it is over B, and therefore the isoparic surface, the constant pressure surface, falls with height. The pressure gradient force points from A to B in this case, and is consistent with the idea that air rolls downhill, as you might expect. And so conceptually, on maps, constant pressure maps, the 900 millibar map, we would see heights for different contours where we would expect that the pressure gradient force is pointing from the higher heights to the lower heights, a concept that fits with our idea of things rolling downhill on a topographic map. On the right, we have the view from above, a parcel starting near A, and what are the balance of forces that cause it to end up traveling east-west, not north-south as we might expect going from high pressure to low pressure. The arrows on the plot are vectors. They show both size and direction. The pressure gradient force in red, the Coriolis force in blue, and the velocity of the parcel in purple. The wind, speed, and direction. Velocity is a vector. It has both speed and direction. And so what we see is that as the parcel begins to move, it accelerates under the pressure gradient force, its speed steadily increases, and as it does, the Coriolis force steadily increases and pulls it to the right. As the parcel is progressively pulled to the right, it rotates, and its direction of motion changes from north-south to east-west. Eventually, we get to a velocity, remember the Coriolis force is a function of velocity, where the Coriolis force perfectly balances the pressure gradient force in the north-south direction, and the parcel is no longer accelerated, it just continues to move at constant speed between the isobars. And so we end up in a situation where parcels move, if you will, as parcels in a river, where the isobars are the banks of the river. And the pressure gradient force would increase if the banks come together because the distance is shorter. And so water travels faster through a narrow river than a broad river. And so conceptually, all these ideas of height, pressure gradients, and how we map pressure surfaces fit with our ideas of fluid flow in gravity and rivers as we see them on Earth. And that's an important part of meteorology, that the concepts we have for our mapping fit our concepts from our general experience so that they become instinctive to us. So again, there's a lot of Newton's laws hidden under here, but I just want to highlight this idea of the Coriolis force growing with velocity till it gets to a point that it balances the pressure gradient force. When the force is balanced, there is no longer any acceleration of the parcel, and it just moves at constant wind speed. And perhaps paradoxically at first, winds travel at right angles to the pressure gradient force in the geostrophic winds. In the gradient winds, we have circular systems, and we can think of this as orbiting systems where the parcels orbit a central high pressure or a central low pressure. I'm just going to focus on the high pressure system here. In the high pressure system, the pressure gradient force is outward. The Coriolis force in the northern hemisphere has to be to the right. If a parcel is moving clockwise around a high, there's a Coriolis force inward, a pressure gradient force outward. But we also have to have, as you know, if you swing something above your head, there's tension, that if you don't keep tension on an object in orbit, it will fly away. If you think about Newton's laws, if you take away the forces, a parcel continues at a constant velocity in its direction without changing. And so if I was to let go the centripetal force at any point, the parcel would just fly away in a straight line and leave the high pressure system. So in a high pressure system, the balance of forces has to be that the pressure gradient force has to be slightly less than the Coriolis force to allow a little bit of centripetal force left over that holds the parcel in motion. In the low pressure systems, you get the opposite effect because you've got now counterclockwise motion around the low. The Coriolis effect is to the right, the outward, the pressure gradient force is inward, and now the pressure gradient force has to be larger than the Coriolis force or effect so that we have a net centripetal acceleration inward holding us in orbit. So there's the balance of forces when we talk about circular motion as opposed to motion in the geostrophic case. It's not talked about in the book, but I want to just take this one step further because there's a question of why weather systems should persist over several days. Okay, you can get circular motion, but why doesn't it just collapse? And this is because cyclones and anticyclones persist because they're stable. And I just want to talk about this in terms of a high and low pressure system in the northern hemisphere. If I take a parcel orbiting a high pressure system, I have a balance of the outward pressure gradient force and the inward Coriolis force. And they are at right angles, they are radial forces, they are in the direction of the parcel to the center of the system. The parcel is orbiting, its velocity is at right angles to those forces, so it just moves around at constant speed in that balance. The Coriolis force is slightly larger so that there's a centripetal force inward holding the parcel in orbit. If I was to magically pluck the parcel out of orbit, now I lose my radial geometry. The pressure gradient force is pointing out radially from the center, but now it's not at right angles to my velocity. There's a component of it northward and a component of it eastward. The eastward component now accelerates the parcel. The parcel now has a larger Coriolis force, and so the parcel now is nudged to the right and it's nudged back into orbit. So this is an example of a stable situation where if I disrupt the flow, the balance of forces in the flow pushes the parcel back to the original motion. Similarly, in low pressure systems, I have the Coriolis force outward, a stronger pressure gradient force inward, holding the parcel in orbit. If I nudge the parcel out, my geometry changes, and I get that the parcel is nudged back into orbit by the balance of forces. In this case, the velocity decreases. The geometry is that the pressure gradient force is acting against the velocity to decelerate the parcel. The Coriolis force reduces, the pressure gradient force pulls the parcel back into the orbit, and so we again have a stable system. The last force that we consider is friction. The role of friction is always to oppose velocity. It's a drag, literally. And so if I look at these three panels, as friction increases, the velocity decreases as I go from left to right. If the velocity decreases, the Coriolis force decreases. If the Coriolis force decreases, the pressure gradient force wins. So on the left, I have perfect geostrophic balance with no friction, and I travel north-south. As I increase the friction, I increasingly travel east-west. The pressure gradient force wins, and the parcel moves slowly towards the low pressure isobar from the high pressure isobar. This is an issue on the surface that we now have, that parcels don't just orbit highs and lows at the surface, but due to friction, they spiral outward from the high and inward to the low, and we'll talk about this a little further in the next slide. I want to just point out that this causes a change in direction in the wind when air travels from different frictions at the surface, from land with high friction to water at low friction. The velocity increases, and because the velocity increases, the Coriolis force increases and yanks the parcel, in this case in the northern hemisphere, to the right, so the wind direction changes, the wind speed increases. We also see this in pressure and wind maps from the lower 48, where winds coming off the Rockies are at right angles. The wind barbs cross the isobars in Colorado on the left, and on the right over Iowa there's lower friction and the wind barbs are parallel to the isobars, and so the direction of wind changes as the friction surface changes. So we have changes in friction both in height as we move away from the Earth's surface, but also across different Earth surfaces. In looking at how we measure the wind, I want to highlight radars again. Radars have been a huge advance in our ability to understand and forecast weather. The precipitation radars we saw using the Doppler effect to reach inside clouds and tell us what's happening in terms of updrafts, downdrafts, wind speeds, precipitation. In what we call clear air, we can also get radar echoes from moving parcels of air and measure the wind itself in clear air. And radars can monitor the wind using three beams. We have three wind directions: north, south, east, west, and vertical. We need three beams to resolve those three directions. So each radar comes with three radio beams coming out of it. The echoes come back from the air, and we look at the Doppler shift, the change in frequency, and we can tell what the wind is, whether it's moving toward us or away from us, and the magnitude of the wind. The kind of data we get is shown on the left. We have time along the x-axis, we have altitude on the right axis, and you can see it's not perfectly uniform. We only get echoes from where we get moisture or turbulence in the atmosphere that creates a good echo. Clear air doesn't have a strong echo associated with it. There's lots of moisture vapor near the surface, so we get good echoes near the surface, continual through the day. And we're just showing this as wind barbs. The highest winds are blue, the lowest winds are purple. You can see there are some zeros in there for zero wind. But these radars are a huge contribution to being able to forecast the weather hour by hour through the day. Radiosondes are just launched once a day or twice a day. Surface wind observations are just that, surface wind observations. We've seen that we need to know the winds aloft. If we don't have vertical motion, then maybe a low pressure system can't persist. If air can't rise, if the winds aloft don't support that, then we're not going to see that low pressure system intensify and exist as a weather system for a long time. So the winds aloft are critical. Having ability to monitor the winds aloft continually is critical in forecasting the weather at the surface. Closing thoughts and summary. Wind is the movement of air relative to a rotating Earth. This is a great question about, it's not just our reference frame as human beings on the rotating planet. We have to think about the fact that we're rotating within the system. The air is moving freely above us. Horizontal wind is governed by the interaction of four forces. We can think of it as the three musketeers and something else. The something else is the Coriolis force, which is due to the Coriolis effect. Not a true force, but a mathematically constructed force to explain the rotation of the Earth consistently inside our balance of forces. The pressure gradient force initiates wind. Fundamentally, temperature differences create pressure gradients, create winds. That's what causes weather on planet Earth and all other planets too. The Coriolis force is used to account for the Earth's rotation, again not a true force. Friction is important in understanding wind variations with both altitude and geography. Changes in friction cause the wind speed to change and also cause the direction of the wind to change. Air is continuous, so variations in horizontal winds are associated with vertical winds. As air piles up, coming into a low pressure system, it has to rise. Now if the winds aloft don't support that rising, then the low pressure system might fail and it might not intensify into a major storm. But if the winds aloft do allow the air to rise, then indeed we will see intensification in a major storm. And finally, while we can measure the winds many ways, you guys are using the Beaufort scale, which, believe it or not, is surprisingly accurate. Radars have been hugely important, as they have been in precipitation studies, as part of our ability to forecast the weather accurately and timely.